we have seen recurrent neural network. It's mathematics, and the session we were supposed to go for the implementation in Python. But in implementation, when it comes, we don't have a separate package for RNN. But the package name is available in the form of LSTM. Also, we have a package available for gated recurrent unit, but there is no standalone package for RNN. We are going to understand the reason why. In fact, LSTM and gated recurrent unit are slightly a sophisticated version of RNN, we can say. Even in the interview, if you encounter these questions about recurrent neural network, so the idea of the long short-term memory and gated recurrent unit evolved as a result of the limitation of recurrent neural network as a standalone model, as it is if it behaves like that. If you look at RNN model, we are going to present the input in the form of a sequence of tokens, isn't it? xt plus 1, xt plus 2, and so on. So when you do the data preparation part, one of the important thing you have to do, first of all, you have to fix the size of your input sequence. Suppose you in your corpus, when you generate so many input sequences, if you find one or two sentences will not maintain the same size of your total length of the X, we are going to pad the sequences with zeros. So zero padding, we keep all the length of your input X, Tx, the fixed. So that means we will say that so first input token, then the second input token, and so on. This will go. And for the recurrent neural network model, when do we experience, okay, and what context do we experience something called as, in our traditional feed-forward model, we have an issue of vanishing gradient, isn't it? Vanishing gradient. The same vanishing gradient is having an effect on RNN model also. But unlike your feed-forward model, here the idea of the vanishing gradient can be appreciated to the context of the length of the sequence. When we see the unfolded version of RNN, okay, when we see the unfolded version of RNN, we have seen that how we to interpret the backpropagation. It's backpropagate over the time. That means whatever the total loss, we have to calculate the total loss once you presented the entire sequence. However, the loss will be calculated at every instant of t. So what is the loss attached to here? What is the loss attached to t plus 1? What is the loss attached to this? And finally, we calculate the total loss. So based on the total loss, okay, it is back propagated over the time t like this. So that is a physically you cannot see this, but logically you can understand the back propagation is with this unfolded version of the t. It is over the time period. We are back propagating over the time period. So what your RNN will experience, basically we are every time we are trying to feed to the model. Hey, this is the current token. Okay, along with that, what we try to feed, along with the current token, always we try to feed. Initially we have used the notation H, then I changed the notation according to the literature notation. A of t minus 1, isn't it? Along with x, every time we append this guy along with x of t, and we were using a common WA notation, isn't it? Common WA notation. We have taken WA outside, and we have appended this weight matrix also to have a mathematically or implementation wise to comprehend in an easy manner. So this guy is going to have every time this a t minus 1 will give, your RNN model will do an extremely good job. Okay, if the sequence length is a very short sequence length. That means whatever the most recent update that happened, what was your immediate past or the last few tokens, what was the major changes that is influenced by the last few tokens. And the next token is highly, okay, the influence of the probability of the next token is highly influenced by the immediate few tokens. Rather, when you consider the earlier stage of the tokens, comparatively these influences will be very less. Because every time you are updating the same AT minus 1 based on the current context. What is the current token? What is the current token? So your AT minus 1 will be acted as your previous memory. So your RNN will face a problem of a short-term memory. It can very well predict the next token, if at all, if your sequence is a very short. But when you go with when I go with the longer sequence, your RNN will not show an efficient prediction, because your RNN is highly influenced by the recent few tokens. Say, for example, look at this. That is why the word embedding plays a very important role. When you look at the word embedding has, they have using hundreds of features. Okay, apart from whether this cat is an animal and all, your word embedding having a characteristic to register even the parts of speech, the characteristic of whether it is a subject or it is a verb. Again, it is a singular verb or it is a plural. So it is going to have a representation for that also. So when your cat is being embedded in the form of a 100 by 1 feature vector, it also has an information about it is a singularity context also attached in the word embedding. And look at, this is my first token, and this is the second token, will go on third token, xt plus xt plus 1, xt plus 2, and so on. Look at this. So the cat which ate few apples and few pears and blah blah blah, and you have so many tokens are there. At this point of time, assume that you wanted to predict how efficiently your language model is going to predict this token. So it has to see, okay, whether this is a singular or plural. Accordingly, this token has to be predicted efficiently. So your RNN model fails to do longer sequences. Okay, it may lose the context. What is the current context? It may lose. So it will see each and every token is very important. There is no dynamic memory, I can say that. It's a very static memory. So every time your t minus 1, the previous memory it's taken as something like a static. We are overwriting on this. Every time we are overwriting on this with a very recent few tokens context wise, this guy is being updated. That means this will be predicted based on a very recent few tokens rather than this, because you can see this cat appears the very early stage of your sequence. So your traditional RNN will not have a strong dependency on for the long sequences. So we have to modify our equation in such a way that, okay, I need to have some kind of a dynamic memory, not as a static memory for AT minus 1. So how we are going to solve this static memory problem experienced by your RNN? How we are going to introduce the dynamic memory with the help of, okay, with the help of a gating mechanism. In fact, while learning the stuff, which order we are learning? First, we learn RNN mathematics, followed by I'm going to introduce you GRU mathematics, and then I'll be introducing LSTM. Because this way you can easily understand the mathematics if I go this way. But to be frank, your GRU idea has emerged. In fact, after LSTM only. Your GRU, gated recurrent unit idea has emerged. Okay. After, see, once RNN is proposed, they understood the long-term dependency problem with RNN. Okay, then people immediately went on this strategy directly without this intermediate stage. Okay. Soon you'll appreciate why this is being introduced. Okay, why this guy is being introduced. And this LSTM is, they were using very complicated, it's not a complicated once you look into it, but in terms of implementation and scalability, it looks very complicated. Okay, to understanding, it's not so complex. You can easily comprehend what exactly this is doing it. But when it comes to implementation in terms of pipelining and all, your LSTM architecture looks very complex for the scalability stuff and all. So people have parallelly devised another less complex version of LSTM has been introduced in the form of gated recurrent unit. So there are certain type of applications people still going for gated recurrent unit because of some of the advantage like less complex, okay, and it's scalable. If you ask me, then LSTM is not scalable. It's LSTM also scalable, but there are certain applications people go with. Again, it's a nature of the implementation over the scientist's choice. If they want to have a very comparatively less complex architecture, they go with GRU. However, if they want to have a dedicated gates for more dynamic, this is going to have 3 gates. Okay, and it is going to comparatively is going to reduce the number of gates. In what way it is going to reduce the number of gates? So in terms of learning, okay, after understanding RNN mathematics, you are going to understand GRU mathematics. Then finally we are jumping into LSTM. But it is evolved. In what way it is evolved? RNN, LSTM, and then GRU. Because that if this way, if you learn, then only you can appreciate the mathematics, not the other way around. So that is why I'm going to introduce you how GRU is effectively handling the long-term dependency problem of your RNN. Because your AT-1 is static. How to make this AT-1 to be a dynamic by introducing a gate. Once again, quickly recollect the basic 3 equation of your RNN equation. Just I'm quickly recollecting it, because with that one equation, if you understand, you can easily migrate to GRU as well as LSTM. But most of the literatures, whatever the literatures available in the internet, I can say 90% of the literatures available in the internet, particularly to the RNN, LSTM, and GRU, they try to explain through a block diagram. Okay, block diagram. Even our presentation also, I have used the block diagram. But I have seen that block diagram will, most of the people, it will try to mislead. Your block diagram will tends to mislead. Okay, you have to go through the mathematics, understand the logic behind the mathematics. Then you revisit the block diagram. Your block diagram does not look so intimidating for you. Otherwise, at the first shot, if you look at the block diagram, you may tends to get confused the moment you look at the block diagram. So I don't encourage. The reason is most of these the literatures, they find quite easy to explain the things using a block diagram, because they simply say in all the literatures, like look at this functionality goes here, this goes here, and this some operation is going on here, these operations are. But they don't explain. Okay, there are some really wonderful blogs, some exceptional literatures are available, but it is very rare and scarce. I can say only 10 to 15%. Who really those blogs really explain the actual mathematics, what is going on, and then they can relate that mathematics to the block diagram. Okay, only this area, that resource is very limited. So that is the reason I wanted to give you the right way of learning your RNN, GRU, and LSTM. Not as mentioned in most of the, even many YouTube videos also, you can see it's a very superficially they touch without giving the importance to the mathematics. because the real beauty of the GRU and LSTM, you can really appreciate how effectively they are managing that 80 minus 1. So what is the first step in we are trying to calculate 80, isn't it? 80. Based on the 80, we will be finally computing OET. So all three models, this is our first focus. So how do we frame 80, and based on 80, how do we frame OET? Okay, so what is 80? 80 is we wrote this 80 as the first activation function G1. So let me better write this expression after taking this WA common out, right? So it is represented as WA and your YT is based on the second activation function. This will be a softmax only. Okay, this activation is tan H, or also you can use ReLU. This is WYA A of T. Okay, for your output stage, you are not appending anything, but here at the input stage, you are appending along with your current input. My previous state memory also I'm appending here. Okay, and then it is we are computing this. But in the output states, once you computed what is the current state memory in the form of AT, you are calculating what is the output response. So this is an expression, isn't it? This is the expression for our traditional R&N. We have got one very nice, interesting way of modifying this equation in GRU is proposed. So I'm going to use a different notation. Okay, just to highlight that this is the equation for the gated recurrent unit. But however, remember in gated recurrent unit and LSTM, the memory state is introduced as not as A of T. A of T is the notation used in the RNN, classical RNN. Whereas the memory state of your GRU is indicated as cell state, C of T notation. But logically, it is the same as what your A of T is doing it, but the notation only different. Because just to quickly identify, this is related to either GRU or LSTM. So both the GRU and LSTM are going to use this C of T notation. Okay, C of T notation. And the C of T is equivalent to, or another way around, our model uses the previous state of AT minus 1, right? So let me say CT minus 1 is equivalent to AT minus 1. Whatever in the RNN unit we talked about AT minus 1. Hereafter in the GRU unit, I will be talking in terms of CT minus 1. Okay, in the GRU, I just changed the notation alone, but literally Imagine your CT minus 1 is same as your AT minus 1. That is why I just put equal. But whereas in LSTM, okay, whereas in the LSTM, I will be maintaining a separate memory for this guy. Okay, another memory I just have memory unit. I will be maintaining something like AT minus 1. So I can say this is not equal to AT minus 1 in the LSTM. Okay, in a broader sense, okay, you just try to understand here CT minus 1 will be treated as equal to AT minus 1 in RNN. But in the LSTM, we have to maintain two different memory state. One is CT minus 1, another one we are going to maintain as AT minus 1. That is the reason LSTM people found a little complex for the implementation. They wanted to maintain as one memory state. Okay, even though one memory state, but they use it in a dynamic fashion. They use it as a dynamic fashion. In a broader perspective, just keep this point in mind. We'll revisit this, why it is not equal here and what way we are calculating this separately. Now, in the same manner, how you wrote AT, I'm going to write, okay, CT equation. How to write the CT equation? Tan H, okay, tan H. You just keep this equation as a reference so that that would be easy. Based on this equation, you can easily write it, the equation. Only the notations are different. Keep this equation as a reference. Here we use W suffix A, right? Here we are using W suffix A because you are calculating A kind of component, but here you are computing a C kind of component. So here the notation goes like this: W suffix C. Your logic and all not changing. Please understand, only I'm changing the notations. Only the changing the notation. At only one place, they were intelligently playing around the equation in the form of gates. So this WC followed by, in greater recurrent unit, your previous memory state is indicated as what? In a regular RNN, it is indicated as AT minus 1, right? Whereas in the GRU, it is indicated by CT minus 1. Already I told you, CT minus 1 is equal to AT minus 1, just like your regular RNN. And your X remains same. Okay, your X notation has not changed. X of T, same as this equation, isn't it? Same as this equation. Plus bias attached with A calculation. So we call this a B suffix, the bias attached to the C calculation. Of course, this equation looks same as this, only the notations are different. But what is a very big deal about this? So here this AT is a very static. Remember, here the AT is a static. Here the C of T is going to act as AT, okay, but this C of T is going to be a dynamic here. C of T is going to be a dynamic. So in what way that this dynamism has introduced here? They have a component called C of T. They are going to modify the C of T based on, okay, to indicate this is a gating mechanism. Okay, to indicate a gating mechanism. This is in scientifically this is called as a toe symbol. Toe suffix U. Okay, we will see what this guy is going to do. Okay, so we have a separate. So it is a scalar factor. Just you imagine this is a scalar factor. So I'll give you an expression for this toe U. Toe suffix U times CT. Okay, CT plus 1 minus toe suffix Q. 1 minus toe suffix Q. CT minus. Okay. So your memory state is not taken into consideration directly. Okay, your memory state, we are doing some operation with the memory states. Okay, some operation. Now I'm going to explain what is this operation. What is the name given for this to U? It is a gating mechanism. Okay, this is a gating mechanism. So this U actually refers to update gate. Actually, this is update gate. Gate in the sense it is going to do some kind of filtering. Okay, it is going to do some kind of filtering. That sense you can understand. It is going to do some kind of filtering process. What kind of filtering process it is going to do? Issue in connections. We are going to have a sigma operation. This is a sigmoid operation, sigmoid function. Sigmoid function. So we are going to have one more weight matrix we are introducing. W suffix U. One more weight matrix is introduced, W suffix U of CT minus 1, comma, XT. So wherever I use this comma is actually the concatenated version. The concatenated version, what is going, it's a matrix operation is performed, isn't it? We are performing a matrix operation. Plus P suffix U. If you look at the original version of this expression, before we take this WA component outside, okay, this is nothing but WA times of AT minus 1, and this is WAX time of XT. These two guys are going to have a matrix multiplication, and this is your X is going to perform a matrix multiplication, the weight. In general, okay, in general, when how do we look at your input performing a matrix multiplication process, that sum of products process? How do you look at that sum of product process with your weight matrix? Of course, it is a literally it's a matrix operation. You are seeing that as a matrix operation, but in the matrix operation there is a logic attached to that matrix operation. Even in our CNN layer also, okay, even in the CNN layer also, how do we represent? This is the trained weights, right? Your two-dimensional weight matrix we call the trained weight matrix. When we actually perform, we are performing a sum of products convolved operation, right? So element wise, you are performing this convolved operation. Your weight matrix is doing some kind of a sum of products operation with your input. That result, how you can perceive, you mathematically you understand what is the process, but I wanted to have some kind of a perception of this calculation. How do you perceive this calculation? Your weight matrix is doing some kind of a sum of products with your input. How do you perceive these mathematical operations? Sometimes this response is high, sometimes this response is low. How do you relate this operation? Okay, your weight matrix is going to, along with the weight matrix and your input is going to perform some matrix operation. Your matrix operation is nothing but sum of products, right? The first row of this weight matrix, and you are going to perform with your column representation of X, isn't it? And when you do this operation, this value multiplied by this value multiplied by this value multiplied by this value multiplied by this, and you take the sum of this. Literally, it looks like a particular operation. That is why I'm just giving another analogy for your two-dimensional perspective. You can easily relate this operation to the context of two-dimensional perception. You can easily relate this. So how do you look at this operation? Sometimes your weight matrix is going to give a higher response. sometimes this weight matrix is giving a lower response. How do you look at this? How do you perceive this result and process? Any idea? Does it looks like a correlation? If your input values are highly correlated with this, your response also, if your response is high, means your input values are highly correlated with these weights. And if your response is low, means they are less correlated with your input. Can we perceive that way? Basically, it is trying to do some kind of a correlation effect. Your input value, it is going to perform a sum of products with the weight. It's trying to literally see how well your weight is being correlated with your input. If you look at the correlation perspective, if you look at this equation, you can very well comprehend the meaning of what is the role of this gate, what is the role of these gating mechanism. So the sigmoidal function, even though it is a sigmoidal function, okay, most of the time the sigmoidal function try to give a higher value and the lower value. Okay, this is, of course, we have an intermediate value, but it tends to give the value, okay, sometimes close to 1, sometimes it's very close to 0. This sigmoid is going to give sometimes the value closer to 1, sometimes closer to 0. Even in between the training process, maybe some value, maybe 0.6, 0.7 also it gives. So that is the reason this is being called as a gate, because when this value closer to 1, we are going to consider something like it is going to allow. When this value is going to closer to 0, means comparatively it is less allowing. Okay, it's hindering. Of course, it is theoretically speaking, it has some effect, but with the hard limit sense, if you look at it like value closer to 1, it's considered as allow. Value closer to 0, it's not allowing. So what is mean by allow or not allow to this context? Whenever you are taking your current token, okay, whenever you are taking the current token along with your this, what CT minus 1 holds? Your past memory, right? Your past memory, CT minus 1. Okay, when your current token and your past memory, it is having a very high correlation effect with this weight matrix. Having a very high correlation effect with your weight matrix. That means the sigma of this higher value, the sigma value is a higher value. When the sigma of this process yields a higher value, what is the logical perception is the sigmoid activation function over this mathematical operation. The high value of the sigma is considered as your current token is having a high correlation with your past memory, CT minus 1. Whether my current token is having a context, it is having a context attached to my past memory or not. If my current token also having a very contextual memory, my current token also have more relation to my past memory, then naturally the sigma of this, the whole process is going to have a value closer to 1, higher value. Assume that your tau of u, when you take with the higher value, say for example this value is high, okay, this value is high, and what happens to 1 minus of the tau of u? So this is 1 minus high value. When you subtract, this value will be low. So you can see what kind of weighting factor is being allotted for CT minus 1 and CT minus 1 and CT.
It's similar to the log loss, right?
Yeah, superficially it looks like a log loss. It looks like a log loss, but here we should perceive in the form of a memory. Actually, the whether I wanted to give high importance to my past memory or to the current memory. Okay, so whether I need to give a higher importance to CT or higher importance to CT minus 1. Is it okay if I give a higher importance to current, and for the past memory, even if I give a less weightage, is it okay? That is what we are trying to see here. Whereas in the previous case, we are maintaining the same 80 throughout the entire sequence. We are maintaining the same 80. We don't have any kind of a dynamic mechanism. So this guy, the sigma is going to tell that which component you have to give a higher importance, which component you are going to give a lower importance. Whenever the sigma takes higher value, say for example, if my current token, it is no way having a connection with my past memory. Say for example, the past memory is what the cat. Okay, the singularity component of the cat. And the current token talks about something else like the or of. Okay, it is not going to talk anything about the cat. Some other words which is no way related to this cat, which is comparatively less significant token. What actually happens in this operation? I told you it is effectively it could be treated like a correlation. If your current input representation, the word embedding of the current token, and the memory unit of tokens, it has a very less match, okay, less correlated. Naturally, the sigma of this guy is going to give me the low value close to 0. So sigmoid function. So when I take the low value to this, so this low value you are giving a weightage. Low value is a magnitude. Say for example, you give 0.1 to CT and 1 minus 0.1, 0.9 scaling factor you are giving to CT minus 1. How do you look at this? How I can look at this? Okay, look at your current memory. CT talks about the current token memory, isn't it? Whereas CT minus 1 talks about my previous state memory. So what it is, your sigmoid function, gating function is indirectly telling you, hey, you keep hold on your previous state memory. Whatever your previous state memory is so important, you keep hold on that. Don't forget the previous state. You should give more memory of whatever your previous state memory about the cat and other subject, about which subject we are talking about. You should not forget that subject. You keep remember that CT minus 1. So how I'm telling that you keep remember that in terms of higher weighting value. At the same time, what CT is focusing on, the CT is focusing on, initially you talk about something about the cat and you are deviating to some other token which is of less contextual meaning, and we are telling that, okay, the current token looks something less familiar to my past memory. Okay, let me give a lesser importance to my current CT and I'm going to give a higher weightage to the previous one. Or I should give a lower importance to past memory, or my current context will be more meaningful than my past. If my current token is having a more meaningful connect, okay, that means I should give a higher importance to the current memory. Comparatively, I should a little bit. It's okay to forget because currently the sentence is talking something about some other characteristic of the sequences. I should dynamically give more importance, more attention towards the current tokens related to the previous token. It is okay to forget little bit about my past, or is it okay to retain my past? So your sigmoid, your gating function is going to tell you how much you should remember in the past, or how much I should, how much emphasis I should give to the current memory. So that way I am going to manage my CT in a dynamic fashion, not as a fixed fashion. Whereas your earlier RNN used only 80, the same equation in the form of 80, but does not have any weighting factor for CT and CT minus 1 or 80 or 80 minus 1. So unweighted, I can say it's the unweighted memory. But here by introducing this sigmoidal gating function, our memory is going to be weighted by the tau u and 1 minus tau u. These are going to act as a weighting value for your current memory CT and my past memory CT minus 1. That is why we call this the dynamic memory. In terms of a block diagram, if you look at the block diagram is given like this. I also given the block diagram as usual, your traditional this is the actual block diagram of your LSTM, but LSTM units are using multiple gates. Okay, but your GRU unit is using only one gate. Okay, what is that one single gate? How it use? Let me differentiate your simple RNN and your gated recurrent unit in terms of block diagram. The functional flow. How you can understand the functional flow like this. The left hand side, I am just drawing your RNN. In RNN, this is my tan H G1. Okay, my first activation function. To compute the response. So what is the output of this? This output is going to give me AT, isn't it? My RNN unit. And your previous memory come from the previous cell unit, AT minus 1. Initially, we don't have this. So initially, we vectorize this as all zeros. So this will be coming for the calculation. So along with your input, so let me take this arrow little downward because it is going to append along with my current token XT. So XT and AT minus 1 were involved with the weight matrix W suffix A, right? W suffix A is entering here. And for that, your activation function is applied to get AT. Okay. So with whatever the AT you have got, what we do with this AT, we take this AT is being scaled by another weight matrix, which is WYA weight matrix is being scaled by this weight matrix. The same AT is going here. Also this AT is going to the next state of your, for the next token XT plus 1. This block, you can continue this block. So AT is coming here. Once again, I have tan H. What is this? This is WA. This guy is coming here. And to yield AT plus 1, to yield this. And this guy is going here along with the WYA to compute Y cap T plus 1. Here, it is going here to compute Y cap of T. Likewise, you can extend it, right? So let me depict this with one single block diagram. Okay, with one single block. So all our both the two equations can be depicted by, this is a standard block diagram, your RNN block diagram. So what modification we have done in the GRU unit? In the GRU unit, gated recurrent unit. So at the beginning itself, let me say here CT minus 1 is treated as AT minus 1. Because only the notations are different, but only difference here is this AT minus 1 is a fixed. Okay, this guy is fixed. There is no scaling mechanism for this. But here we are going to have some scaling mechanism for this guy, AT minus 1, or to the context of GRU, strictly we call this as a CT minus 1. As usual, we take the previous state. Okay, the previous state will come along with your current token XT. It is being weighted by WC. Okay, but just so the notations are different. Here W is acting the same role. So tan H. So this tan H is yielding what? the tan H will be yielding your regular CT output. So we have another connection going here. Another connection. Even for the sigma also, what we take for the sigma also, we take AT minus 1 and same XT. But for this side, we have a separate weight matrix called W suffix U is going on. Okay. So that is why I'm extending the connection over here. That means the same XT along with AT minus 1. It is weighted with W suffix U, and this time the sigmoidal activation function, which is going to act as my update gate, and it is going to give me the output called tau of U. What is the nature of the tau of U? The nature of tau of U is sometimes it's close to 1, sometimes it's close to 0. Okay, intermediate value also you'll get. Whenever the value closer to 1 means it is allowing. That means your tau U value is a higher weighting value. Obviously, 1 minus tau U value will get a lower component. If tau U is closer to 0 means tau U component is 0 and 1 minus tau U component will be higher, complementary. So along with this, the tau U, what I do, this CT is being scaled. Okay, this is being scaled by this guy tau U, and you are going to have an effective, the more effective, the scaled version of, I'm going to call this the scaled version of the CT you are going to get, or gated version of CT. So let me write this CT as a gated version of CT. So naturally your CT minus 1 also, it is being scaled effectively. And using the CT, finally the CT will go through the same process. Okay, the CT has to go through your output weight matrix WYC. Okay, WYC to yield. Here we have a softmax to yield the final Y cap of. This is the Y cap of. So this component is an additional component here. It is actually giving importance to my CT. What is the weighted memory of my CT? Unlike here, it is just using the unweighted memory of AT is going. So this time, this CT is going to act as my CT minus 1, right? For the cross memory for the next token, right? Since you are updating this guy, right? Every time you are updating the previous memory in the form of sigma, it is going to be like a more dynamic, your memory is going to be more dynamic rather than your unweighted. Throughout the journey, your AT it is just going forward without capturing the content of the current content of XT, without capturing the current content. Simply your previous memory is just keep updating it. It is not having something for dynamic memory. See, hey, look at this. The current context is it's more related to your past memory, so you should be weighted high. Or the current context is less relevant to the current your previous memory. Let us not that much update change your CT. So the cat afterwards, so many tokens were less relevant to this. Okay. And after sometimes I need to predict some token which is going to describe something about my subject. Okay. So first I talk about another example. Let me give another example. Say for example, Ajay is working in France. Okay. Then I change the topic to something else. Okay, I change the topic to something else, and some other sentence is coming which is not actually describe anything about the Ajay. Maybe as part of his work or something, some other sentences. So Ajay is working in France for maybe 10 years. I explained it, and as part of his work, and he recently he relocated and so many things. which is very less relevant to this Ajay and France. And after few tokens, now Ajay speak fluent. Okay, Ajay speak fluent dash. So I need to fill this. So Ajay is working in France for so many years, and then the next sentence, these are the tokens, okay, related compared to the memory unit of Ajay and France and stuff like that, according to the subject and the France relevance. As part of his work and all, it has a lesser context. Here you don't your model is indirectly is going to tell that, okay, you don't need to retain every time for each and every of these tokens. You don't need to retain this memory of this CT. You don't need to modify the memory of the CT. So the memory of the CT will be less affected or less influenced because of the less relevance token. In context with your past state memory, CT minus 1. If your input tokens are less relevant, your CT will be less adjusted. And on the other hand, again, if I'm going to talk something about the Ajay, again, the same subject is coming again. It is going to be your model will be wake up. Okay, again, the sentence is going to talk something about the subject, my past memory. Okay, your CT has to be okay updated to the most recent contextual. That means this time your CT is going to be weighted heavily because 0.9 is a scaling factor, right? Your tau u will be giving a higher weighting factor because it's highly correlated with my past memory. If the input tokens are less correlated with my past memory, your CT will be less adjusted. Otherwise, your CT will be more adjusted. So whether I wanted to less adjusted or more adjusted, it's being controlled by your tau of your unit. That is why it's being called as a gated recurrent unit, because you have a gating mechanism to control and update your CT to be more dynamic based on the current context. So that way, even though if your sentence is too long, your CT is going to have a more dynamic memory rather than a static memory. So even though the relevant tokens are irrelevant tokens, your AT is being updated in a same manner. So when the same subject is being introduced after several tokens, it does not capture the context, whereas this guy is going to have the context is being retained relatively better than your regular RNN. Whereas in the LSTM, people have introduced what they have done. Okay, why you are using the same one single gate to control my present memory and the past memory? What people have suggested in the LSTM unit, why don't you keep a separate gate for, you maintain one separate gate for this fellow, you maintain one separate gate for the current memory and another separate gate for the past memory. This is being introduced in the LSTM. In fact, this is what originally suggested. This is what actually originally suggested after your RNN. But over the period of time, what people have researchers has done, they just approximated. No need to maintain two different gates for the CT minus 1 and CT. We can handle very effectively even with one single gate itself. You can manage something like, okay, if this goes higher, you gives a complement of this. If, say for example, this is 0.9, obviously this goes lower. Or if this guy goes higher, this becomes complement. So they just very well approximated the LSTM unit, which uses a dedicated gate for CT and CT minus 1. They use one common gate. But however, you should know how they have used a dedicated weighting factor for CT and CT minus 1 in the LSTM unit. Now we have, let me write the equation for the LSTM unit, how the mathematical equation, how to represent the mathematical equation. And moreover, remember in the LSTM, I have to keep track of something called, okay, AT as well as CT. Whereas in the GRU, we have treated these two guys same. Okay, we have treated these two guys same. But in the LSTM units, I'm going to maintain AT separately and CT separately. Okay, we are going to understand what is this AT fellow and what is this CT fellow. As usual, like your GRU, let us write the first equation of CT equation. We write like a GRU, tan h of W suffix C. This equation looks same as your GRU. WC AT minus 1 XT What is the difference? Same as this, isn't it? Same. Sorry. Here. This is in GRU, we have written the equation like this, but have you noticed the important difference? In GRU, I have written C, I wrote C of t as a function of, okay, as a function of CT minus 1 and XT, but here we are writing C of t instead of as a function of CT, I'm writing as a function of your regular RNN. Actually, your regular RNN, we were using AT minus 1 XT, right? That's why all three equations are written over here. First, we wrote the equation AT minus 1 XT. Because the reason here in GRV, we treated CT and AT same. That is why, okay. So it doesn't make any sense whether I write this equation as AT minus 1 or CT minus 1, because in the GRU, both are same. Both are treated same. I'm not recording these two guys separately as a separate entity. But here in the LSTM, I'm going to record this as a separate entity. So that is why I'm writing this equation as the original version of RNN. I'm writing as my previous memory AT minus 1 along with my current token. First, I'm writing the equation for C. Let me give some space in between. Same manner your GRU, how we updated. We are going to update. This is called a cell state. Hereafter, I'm going to call this a cell state. And A, you can call it as a hidden state. See, literally both are memory only. Literally both are memory. Soon you'll understand what kind of memory it is. Okay, we are maintaining a different memory for current and past. Okay, current and past. That is why we are representing in two different memories. Now CT is represented as update gate times. Okay, update gate times. We are introducing a scaling factor for my current memory in the form of tau u, same as your GRU. But look at this portion. This portion is different. In GRU, what you've used 1 minus tau of u itself we have used, right? Whereas in the LSTM unit, instead of that, we are going to use a dedicated gate for my previous state. So let me call, since it is a previous, so it is being called as a forget gate. How much I should forget from the past? Okay, how much I should remember in the current? To indicate that, so this gate is being called as the forget gate, and this is the update gate. How much I should update the current? How much I should forget the past? Okay. Even you can logically you can correlate this 1 minus of tau u times of CT minus 1 can be interpreted as this weighting component over the CT minus 1. It's literally you are giving some weightage to your past memory mix. This weighting factor is considered as some forgetting component. Okay, some forgetting component of CT minus 1. But here specifically we are using that notation tau of f. But tau of f will be, it uses a unique separate weight matrix. You will remember this. Whereas the GRU, the same weight matrix is remembering both. Okay, we were using only one single weight matrix called W suffix U is remembering both. But here in the LSTM unit, it's two different weight matrices. One dedicated weight matrix for this, another dedicated weight matrix for this. So we call this the forget gate times C T minus 1. You already familiar with how to write this. Okay. So first let me write this. To U, all the gates, remember all the gates are going to use the sigmoid weighting fraction. That is why, because the nature of the sigmoid is, it is going to give a higher weightage or lower weightage if the value is closer to 1. Otherwise, it is going to suppress. So tau of U is represented as the sigmoidal function. Okay, look at here. Dedicated weight, same as your GRU. Okay, same as your GRU. W suffix U, AT minus 1, comma, XT plus bias of this. And I have to define this, right? So we have another gate called forget gate. This again, forget gate is defined as a sigmoidal function. Here we are using a dedicated weight for this called W suffix F, AT minus 1, C plus B suffix F. Okay. Apart from these two guys, we are going to give one more gating mechanism. Here I have used one common gating mechanism for my past memory as well as the current memory. Okay, one common gating mechanism for CT minus 1 and CT, in fact AT minus 1 and AT. Whereas in LSTM we have a dedicated 2 sigmas are there are 2 gates are there. Apart from these 2 gates, there is one more gate is being introduced in the output side. Okay, that is another uniqueness when compared to GRU. One more gate is being introduced in the output side. So let us see what is the purpose of that. So in the output side, there is one more gate. That gate is called as, okay, the gate for the output. So the gate for the output again is being represented as sigmoidal function. We have a dedicated weight is going to have a memory for that output side gate, W suffix O, AT minus 1, XT. Look at this, all 3 gates, it is looking at the correlation, how well my current token is correlate with my past memory. Still, you can treat this AT minus 1 as your past memory. So plus the bias representing this output gate, so B suffix O. So now you'll be wondering where this guy is being used. You understand how this tau U you use and the tau F is used. Can you notice this tau U and tau F is used to update CT? Okay, update CT. That means we are going to use your AT, right? AT also going to get updated. AT also going to get updated with the output gate tau U times. Okay, tau U times. Finally, your CT is going. Where is the path of your CT? Your CT should reach. Okay, your CT should reach to the output side to yield Y cap, right? So before your CT reaches that zone, it is being weighted. It is being weighted by so let me write like this. how to logically understand the context of AT factor and how to logically understand the context of CT factor. Mathematically, it is okay. How we are updating your CT is based on AT, first of all, right? Your CT is based on AT. We are updating CT as well as we are updating AT. What is the logical connection of this? Your CT in the LSTM unit is considered as long-term memory. Okay, your AT, in fact, CT and AT are memory units. We are giving some logical name to these guys. This is considered as a short-term memory. Because unlike CT, I'm not updating AT and AT minus 1. Look at this here. For CT, we are updating every time we are updating current, how much weightage I should give for the current, how much importance I should give for the current, and how much portion I should forget for the past. So one side you keep track of your long-term memory, another side you keep track of your short-term memory using a different dedicated weights. That is why, even though LSTM is a complex, of course, they were using a more dedicated gating mechanism for each characteristics. Of course, in terms of the refined prediction, obviously LSTM will outperform GRU only. But why still people are going for the GRU? For the simplicity. For the simplicity, if for the simplicity and for the scalability, there are some application I'm not going to use a very lengthy sequences and all. Okay, my sequence is not too lengthy and all, but still you can manage very effective with the GRU itself. You can go with the GRU. No, my sentences are too longer and all. It has to understand the too longer contextual meaning of the sentences. It's all depend upon to what context you are going to implement. Say, for example, I'm implementing this language model to the email reply. I'm going to do this for the email reply. I can very well manage with the GRU itself, isn't it? Most of your email reply and all, we don't write very longer sentences and all. Most of the sentences are very shorter sentences. Even I can effectively predict the next token with the GRU unit itself. But unlike an application like I wanted to build some chatbot. Assume chatbot user will be querying the model with too longer sentences and all. So your language model should understand what the customer has asked at the beginning, and in between I just deviate my question to something else I'm asking. Again, I'm ending the question with with some other context. I'm ending the question. So for these kind of things, definitely I have to go with the LSTM model, because your LSTM model has a dedicated memory for the long term as well as the short term context. Now I'm going to give a logical name for each, even though it is called as the forget gate and this update gate and all. Okay, what is the logical meaning we can attach to these mathematical component? So this update gate, CT, right? Update gate is working on the CT, right? This operation can be understood as any idea? What is the role of this operation? How we can understand this operation? Shall I say adding new information? Okay. The new information. This is treated as adding new information. This one, it's going to work on irrelevant info. That is why it's being called as forget gate. Suppose if your past is something like irrelevant, your forget gate need to be suppressed. So that is why it's called as your forget gate. So this component update gate, updating any new information, any new context in the meaning of the sentence. So this is adding the new information, and this is irrelevant information. And what name we can give for this out gate is, what is the logical name we can give for this output gate is. Here we are just adding the new information. Okay, we are just adding the new information. Whereas the role of this guy, it is giving a weightage. Can you see at the end of the day, this guy is giving a weightage. Once again, it is giving a weightage to C of t, isn't it? Here, this is updating the current information, but here it is again, it is giving a weighting factor to the C of t. If the relevance is more, okay, if the current context relevance is more, the role of your output gate can be logically understood as update, okay, update relevant info. Here we just adding the new info, just adding the new info, and this is being, once again, it is being scaled. This is once again scaling your C of t at the end. The scaled version of the C of t, we are updating this as a AT, because you are using only C of t. That is why your A of t portion is called as a short-term memory here. Whereas the C of t is, it's not only having the current, also it uses the past state. It is being called as a long-term memory. Your A of t is using only the current state of C of t unit. It is being logically treated this as a short-term memory. So in one side it keep track of C of t, another side it keep track of A of t. So when you move from one block to another block, like how your A of t is keep traveling between one block to another block. One block in the sense, here you should understand the time step. So like how your AT minus 1, it's carrying forward to the next time instant, and this AT minus 2 is carried forward to the next time instant. Like say for example, sorry, this is if I say this is my xt, I say this is t minus 1, this is t minus 2. Okay, if this is my current context, if this is the xt, this is my past. Or let me start with the xt in the first block. Suppose I start with xt in the first block. Previous state, I don't aware of the previous state. I have AT minus 1. Similarly, something I have to initialize as my, initially I'm going to say my long-term memory is all 0. Okay, my short-term memory also 0 for the first instant of xt. So we have the mechanism to compute. Okay, we have the mechanism to compute what is the current state AT, and also we have a mechanism to compute CT, right? Your CT is computed separately and AT is computed separately based on the equations what we have seen. Once this guy is computed, okay, of course, based on the CT and AT, your final y cap of t is being computed. The final y cap of t is based on the combination of CT and AT. So once this is being computed, which is used to each state output, also this guy is being carried forward to the next state xt plus 1. For the next state token, your AT is being carried forward to, because this is going to act as my past memory to compute my current t plus 1 and my current ct plus 1. Whereas in the GRU unit, we don't have a separate memory of this AT. Only this guy alone we carry forward. Only this portion alone we carry forward. But in the LSTM unit, we are carrying forward these both my short-term memory as well as the long-term memory. We are using the CT itself as a long-term as well as a short-term memory. We are using it in a dynamic fashion. But in the LSTM unit, saying that no need to use the same scaling factor to U itself to operate the current and long-term memory. Better use a different gating mechanism for AT and many to many. So any application in LSTM, you can easily put into any of these three categories. So let us see how to appreciate first, let us see many to one. Can you give your a thought process on many to one? What kind of application will come in many to one? Any idea? Any suggestion?
Maybe classification.
Sentiment analysis.
Yeah.
Even we have seen, right, the restaurant food. Okay, not good taste, not good service and all. So you are giving your input sentences as your you will be giving your input sentences like this fashion. Like what is my X first token? What is the first token? Then I present second token. What is the key point you should understand here is it important for me to get Y of 1 question mark? In many to one, this is meaningless, isn't it? This is meaningless.
Yeah, I think like TF, IDF or stuff like those kind of calculation will make more sense.
Yeah, see, this is your overall LSTM block. Okay, inside LSTM block, I'm just unfolding at each time step how to understand this LSTM block. I'm unfolding it. But how your LSTM is going to accept your input? It's going to accept, okay, the service is very slow. This is the sequence of token your model has to receive. Really, your model need to predict after the it is important for my model to predict after it has to predict service, or after service the next token. Is it that is the duty of this model? That is not the purpose of this model, isn't it? Of course, your model will keep track of the sequence. How will it keep track of the sequence? Your model will keep track of the sequence in the form of, just now we have seen, right, that is in the form of memory units. It is keep track of this in the form of A of T short-term memory and the long-term memory. Okay, that is in the form of your memory units, AT and CT. But really, this Y cap of output is not important in this application. Hope you got it. But what is important here? What is important here is, so I present the complete sequence at each time step. At each time step, I really no need to calculate what is my Y cap of 1, what is my Y cap of 2. I'm not going to compute here. Okay, rather just you are placing your input token and so on. This is my last token of my input sentence. It's always represented as TX, isn't it? Whenever the moment I present this, I complete my entire sentence. Okay, I complete. In the meanwhile, all your AT and CT keep travel taking as the previous state, and it is working on. For the next state memory, it is working on AT and CT, isn't it? See, for AT plus 1 calculation, I have to depend on my previous, isn't it? Similarly, for CT plus 1, it has to work based on this earlier state. So at every state, Y cap of T is not important for me. But towards, once you finish it at the end of the token, okay, towards the end of the token, now you may ask the question how model will understand the end of the token. We have a mechanism in the data preparation part. Okay, we have a mechanism to give start of sequence, okay, end of sequence, start of sequence and end of sequence. When you tokenize your vocabulary, okay, this also be part of the vocabulary. It is going to create a unique identifier for this also. Start of the sequence, end of the sequence. Your model will understand, okay, this is the last token. We have received the last token. So this has to be given to understand the sentence is over. Okay, once I have given the entire thing, and my model should start calculating. Now only it is going to compute this Y cap. Okay, this Y cap probability is going to compute. Here the question comes, what will be the size of my output here? What will be the size of the output? As I told you, you can use this many to one model, okay, to understand and classify what is the nature of this text sequence. Okay, if it is a sentiment analysis, you wanted to just classify the test sequence. It is a positive sentiments or a negative sentiments. You can treat as a binary classifier. Okay, 1 and 0. So in the output side, only 2 neurons. Okay, in the output side, only 2 neurons, and your model will give you the probability. Whenever the first neuron gets the higher probability, it's a positive sentiments. And you can give a negative sentence, and you can try to give the representation like 0% probability for the first neuron, 100% probability for the second neuron for the negative, and this is for the positive review, negative review. Or you don't want to just to simply say that positive or negative. No, I want my model to predict the star rating. Let my model predict the star rating. Whether it's a 1 star or a 2 star, 3 star, 4 star, 4, 5 star. Okay, and again, this is like a multi-class problem, right? Same sentences you are giving it. So, but you have to categorize it. Okay, what kind of sentences more likely people will give 1 star? What kind of review people will tend to give 2 star, 3 star, and 4 star? First of all, you have to segregate your training record accordingly. Then you have to categorize your input reviews also like that, multiple category, and this output will be one hot encoded according to each sentences. You can train the model. So the point here is your loss function. Your loss is calculated only once you complete the entire sentence. Once you complete the entire sentence, only your loss is calculated at towards the last one. Suppose you are giving a positive sentence, but your model has given higher probability. Okay, your model has given the higher probability 72 for the 2 star. Okay, this is dedicated for the 2 star. Okay, and so my loss is very high, right? You have to for the sorry, this is the say for example is a positive review, and your model has given the higher probability for this, and for the 5 star, it is yielded a very low probability for it. So my loss is very high. Naturally, your model will try to adjust the weights to increase this probability and to decrease this probability. So that way your model will learn. Okay, only you completed the sentence, then only it is going to compute your output. Any other example you think of practical application? Any other practical example can you think? Even the news group, we have used the news group. Still, you can operate with LSTM also, isn't it? Many to one design.
Content categorization, maybe into categories.
Yeah, political news. Yeah, political news or sports news. But strictly speaking, that's order. It's least important. Still, we were able to manage with even feed-forward model, right? But having said that, you can use many to one model. Can you think beyond text? Can you think beyond text? See, this is the place you have to apply your creativity.
Sir, forecasting.
Very good. Forecasting. Here, see, I have provided the building block to you. Imagine like your fixed building block. Okay, I have given, this is the way you can construct. You can come up with very beautiful models using the building block. Whichever the way you can construct, you can come up with interesting idea, interesting. You can play around with any kind of application, you can easily play around with this. But all you have to spend time only on the data preparation part. Once the data preparation part, you have the core architecture is going to be the same, how you are going to use your many to one architecture and one to many or many to. We have a same pattern. Okay, that is not going to modify. According to your application to application, you have to prepare your data set. So that is the time Vijay mentioned even numerical time series forecasting. Okay, one of the example even I will be showing that. So if I give the last 1 week pattern, okay, if the last even stock market, any numerical data sequences if you give, if this is the pattern, okay, your entire LSTM model trying to understand the long-term memory and short-term memory of the pattern. Last beginning of the month, how was the trade, and middle of the month, how the trade was. It is static, and again towards the end of the month, the trade has there is a slight increase in the trade. Okay, so understand the 1 month pattern of the trade. If you wanted to forecast what is the tomorrow's trade, so you have to give the combination, like your training record should be like this. Okay, if the trading values are like this, okay, the next day, every 30-day value, if you give maybe the 31st day as your target value, you can prepare your input and output sequences like this, right? For the sequence, this is the output. For the sequence, this is the output. For the sequences, this is the output. So in this case, one slight difference in your output, your last output calculations and training mechanism. What is one when compared to the previous example, sentiment analysis? What is the major difference? Can you think of the forecasting example?
We will be forecasting multiple outputs.
That is that you can do it. See, repeatedly I'm going to ask this model. Okay, see, for example, the last 30 days I have used. Tomorrow, what is tomorrow? It is Friday, right? Okay, I'm asking the model, hey, tell me what is the Friday's Google stock price going to, what is the open price tomorrow is going to. Based on the 1 month pattern, my model can say that. Okay, and once you have generated the forecast for tomorrow, I can including the tomorrow value, the recent 30 records, you can give it as a chain of repeatedly. You can call the LSTM block again and again in a loop. It is going to give you the next day, like that. But this is at one value at a time. It is going to forecast because it's a many-to-one model. Okay. But no, at one point of time, I wanted to give the next 3 days value or next 5 days value. So you have to modify your input and output arrangement like many input sequence and many output sequence. Likewise, you have to train it. But here I have trained the model to predict one value at a time. So you call the model to predict one value at a time. Once it predicted tomorrow Friday's value. Okay, let us assume a shorter sequence. So it is going to use the past 3 days value. Okay. Today is the Thursday value I have given, Wednesday value I have given, Tuesday value I have given. So based on Thursday, Wednesday, and Tuesday, it is forecasting Friday. Okay, once I got the Friday value, Wednesday, Thursday, Friday, because Friday is already forecasted, I can use it for the Saturday forecast. Same model, I can repeatedly call. Okay, whatever the value is being predicted, that value I'll be feeding as my third value, and I can use it for the Saturday prediction. Then Thursday, Friday, this Saturday prediction will come to predict the Sunday prediction. Again, Friday, Saturday, Sunday, I can use it for the Monday prediction. So this is just a one for loop. I can write it to operate this again and again. But if you at one point of time, my model has to give the next 3 day prediction or next 1 week predictions. Accordingly, you have to prepare your input and output sequences. Okay, so Monday, Tuesday, Wednesday, Thursday, you have given as input. Then Friday, Saturday, Sunday. This is the target. For the past record, you have to prepare it. Similarly, you have to create how many input sequences, how many output value you have to prepare. Like that, you can make it as many to many model. You can build like that. Okay. So any other application other than sentiment analysis or number forecasting for whether you can forecast temperature or a trading value other than text? Other than text, one example I have told, and for numerical, another example you have told. Okay, I was talking about the nature of y cap of t when you train. What is the major difference for the stock value forecasting? What is the major difference when we were discussing the example with sentiment analysis example? What is the major difference?
It will be a regression value, right? It won't be.
Excellent. This was I waiting for. Your loss function is different. I don't use a entropy loss function, isn't it? There it's a probability, but here it will be acting as your mean square error. Your loss function is trying to reduce the loss function, update the weight to the context of mean square error, because your model is working into the context of a regressor context. But here you are classifying your text based on the sentiment. It works like the log loss. That is the major difference. Okay. Now, any other example? Any other example? Can you think beyond text and this forecasting? What about a musical note? Musical note. We have a sequence of musical notes, isn't it? Musical notes are there. So your musical notes are given in a particular sequence. You say this one note and like this, a particular raga, okay, as a sequence. Each your note can be tokenized. Can be tokenized, can be numerically encoded. Not a big deal. We have a mechanism to encode it. But of course, we may not use the word embedding, but I can use a one-hot encoding. Okay, I can use a one-hot encoding. But compared to the word corpus, this musical notes is not going to have a very 10,000 corpus or 20,000 corpus, 50,000 corpus or billions of corpus. Because we know that musical notes are going to hardly take a few A minor, C sharp, C minor. Likewise, we have a limited set of notes are there. Okay, even you can consider there are some standard 40 notes or 30 notes you wanted to maintain. Easily, you can encode these notes as a one-hot encoding representation. And if I train a model with a sequence of these nodes, okay, it will understand the order in which pattern these notes are there. I can train a model to predict the raga. Possible? What raga? Because one raga to another raga, the order of the notes and the way I use the notes and all, with definitely one music pattern or the genre at least. Even you can train the model to differentiate the genre, whether it is a rock or a hip hop or what is the Hindustani. Likewise, you can even use the sequence of a musical notes. Okay, and you can ask with output side, you can give one single label to understand what is the raga or what is the genre of it. That way, I can use this many-to-one model. So applications are plenty. If you apply your creativity and you can think of at least a 1 dozen applications, you can think of it. Even you can use some biological signals also, but it's a little hard because your biological signals are too redundant, samples are there. But other applications like speaker identification, speaker. Suppose I have a speaker recognition system. You have given one sequences, and based on the sentences what you speak, I can train a model to make one single decision in the output. Say for example, I have told you some voice-based control system, robotic application and all. You train a model whenever you speak a list of a sequence of tokens. Okay, output should train for a particular application. Another set of sequences when you speak. Okay, this time your input is going to be my speech signals. And that speech digital samples of my speech signal should be passed as an input, but not as a raw version. Whenever you need to work with the speech signal, you have to process your speech signal. Should go to some processing. Maybe you can apply to some one-dimensional CNN layer. That output as a featurized representation of this one-dimensional. Okay, if the speech signal having this order of the features, and maybe you can train to the label like this. If this order, if the characteristic of the pitch and the tone and the frequency of the voice comes like this, you should recognize. You can make the model to recognize this to take this action like that. So you can think of text application and numerical simple forecasting application on the speech and the raga musical notes applications are playing. Can we do the reverse thing? Can I do the reverse? If I give a genre, okay, if I tell the genre, hey model, generate a musical notes for the Hindustani raga, model can do that, isn't it? But for that, how I have to frame my architecture? So I have to frame the architecture like one-to-many architecture, right? How your one-to-many architecture is going to work? You are going to have the first token. Mostly the first token is going to be the trigger, only your trigger token. So you have to represent your input as, say, for example, the raga name. Okay, so each raga name you have to have some vectorized representation. Okay, raga 1, raga 2, raga 3, some different genre of the music, maybe genre, whatever it is. You have embedded some one-hot encoded representation. Only you have to feed only your trigger token. Just you have specified the raga name. What this guy here, my y cap of 1 makes sense, isn't it? Because this guy has to generate the sequence. It has to generate the sequence. The moment you give the trigger token, it starts generating the first note of it. You have to train in such a way that, okay, whenever I use this raga as a trigger token, what should be the first note has to be produced? What should be the first note? What should be the second note? What should be the third note? Which order it has to be produced? That can be given as a one-hot representation, right? Say, for example, totally you have around some 40 notes. Okay, so when this trigger token is that, which is the first note token this guy has to produce? And the memory units will be transferred to the next time instant. A of t as usual and long-term memory CT will be transferred to the next instant. Initially, AT minus 1 is 0 and CT minus 1 will be 0, and AT will be for carry forward and CT will be carry forward. Now the question here is, what will be the input for the next time? That's the question mark, isn't it? Can you give me an idea for this? Help me with an idea for it. Because you have only the trigger token, because it's a one-to-many application, right? One-to-many. What is the idea for this?
Y of 1.
Ah, excellent. Your Y of 1, I can wire and give it to this. And this guy is going to give me Y of 2, and I'm going to give to the next time instant. And Y of the next musical note and give this to this. This can be, you can use it for the text generation also, right? Text generation. One trigger token, and you can ask the model to generate a poem. Generate a poem based on the trigger. Okay, what genre you wanted to generate a sequence of the text. If you give one trigger token, you can generate a sequence of text. You can generate a sequence of musical. You can, what else we can use it? Any other interesting application can you think of?
Autofill.
Sorry?
Email. Autofilling. Like text autofilling. Like if you start writing email, it will be predicting the next 2 words. Right?
That is many to many. I'll tell you. That will come under many to, because my input sequence I have, the entire sequences I have to train the model. Okay, not just a trigger token. Actually, your model uses the entire training sequences. I have to train each sentences completely. So in that case, your many to many itself will be categorized into two categories. Okay, one is many to many. One case is whenever I keep tx is equal to ty, the length of the tx is equal to length of the ty, typically as a language model. So what we call this is a language model. Language model. Your email autofill and your text autofill and all. I have to train the model with the complete length of the sentence. Say, for example, my first token is a Mary. Okay, Mary. And what is the expected output for this? Had. Okay. So what is the next token I should feed to the model? Had. What's the next token I should feed? The target should be little. Okay. Every time I have a had as a target, Mary is the input. So each stage I have to calculate the loss function, and the total loss has to be calculated. So my first token x of 1. Okay, this is my had is the expected output, and we have to see what is the model is producing. Mary had it. Now this model is going to learn the sentence. Mary had a little lamb. Like in you can take your email conversation and you can train what are all the standard sentences that happen in your standard email conversations. Whenever you start replying in any email. So most of the common words are like, say, hope you are doing good. Doing good. Because in the embedded vector, good, well, okay. So these are all the words are placed very close to each other in the word embedding, because the meaning of the good, well, and all. So more likely after doing, it's try to autocomplete with the good or well. And for that, I have to train my model. Already, this model should be trained with the standard sentences like this. So what is the first token for this token? What is out? For this token, what is out? So even any lengthiest sentences you can give. So I would appreciate, if you could reply by the end of the day. These are some of the standard sentences we use in our official email conversation. So I can train these kind of lengthy sentences like this. So model has been trained, whatever the kind of sentences you wanted to train, these kind of, so this is my tx is my length of my input sequence, and so we have a standard length of y, because at every stage you wanted to produce y of 1, y of 2, y of 3 for the given input sequence. Okay, so your input sequence, what is the corresponding y? So in a Mary had a little lamb, your tx is represented as, okay, like Mary had a little lamb. Okay, and or I can say not the total size of the token is tx. Maybe this my xt flow goes like this. Similarly, my yt flow had a little lamb. Okay, EOS. So this is the way your typical language model works. Your input, you are training the input model with a sequence, and output also you are expecting a sequence. So at every time instant, you are expecting the y. Every time instant, you are expecting the y. So hope you are able to differentiate one to many. In one to many, only we give a trigger token. Okay, your model is start producing the sequence. Y of 1, y of 2, y of 3 sequences start producing it. And many to 1, okay, you have x of 1, x of 2, x of 3, and so on. But your model is going to give me my final y at the last. Okay, a final y at the last. So it is, I don't use ty because it's only one value at the output. So only y cap. So this is many to 1. This is 1 to many. Whereas in the many to many, okay, both combination of both x of 1, x of 2, x of 3, I have to give at the same instant y of 1, y of 2, y of 3. Because first of all, I have to train the model, right? The actual sentences I have to train the model. After training only in a production environment, okay, in the production environment, what happens? Your production environment, you try to give your input, maybe how or when you give these two values, maybe your model will try to give another 2 or 3 tokens for you. Try to autocomplete a few tokens. So in the production environment, what happens is whatever the value predicted as one time instant, that value will be fed again and to produce the next token. Whatever the value predicted by this guy, it is being fed again to the next. That happens in the production environment. But during the training process, first of all, your model should understand the sequence of the text, right? So you are training during the training how you have to wire the architecture. During the production environment, whatever the value is being predicted at a particular time instant, that has to be fed again to the next time instant to produce the not just one token, right? It's a sequence of value it's going to predict. So that wiring we have to do it to the content after training. Once you complete the training, I have to reconfigure my model for the production environment. So that all we will be seeing in the coding part. So how we have to reconfigure the production environment. One final special case is there. Okay, many to many, where your tx is not equal to ty. So here I'm saying my tx is not equal to ty, not to the context of the length alone. I'm not talking to the context of length. Don't focus only on the length. Here I'm just focusing on apart from the length. Okay, apart from the length, of course you can in fact you can do the padding and all and you make the length equal. That's not a big deal. What I mean to say here is your earlier many to many is okay, your actual the sentence, your English sentences, you are making your model to understand the flow of the English sentence. But many to many, your tx representation is different and your ty representation is different. That is another case, fourth case. The best example for this is language translation, machine translation, what we call as a machine translation. Okay, I have an English sentence, but my output is a French sentence or a German sentence. This also comes at many to many. Okay, but you cannot train, unlike your earlier model, I cannot train like this. Okay, first I have to make my model to understand the flow of my English sentence. The flow, I have to understand. Then for this flow, what is the corresponding translation? So this comes under a special case. Whenever your input sequence and output sequence representations are different, okay, different. Your earlier representation was called as a language model. Just you are training your LSTM to understand the sequence of English. What we call a common name for that is called as a language model. Any language model, you can train your email text sequences, or you can train your model to understand not only email. There are so many applications nowadays we are trying to do autocomplete. Texting and so many other some Twitter feed and all those cases. Wherever you have a scenario like this case, your input sequence is different from the output sequence, not based on the length, I'm telling. Okay, the contextual differences are there. Language, one language to another language. Even the chatbot also comes under the case. The chatbot, actually, the language translation, there are two things has to be taken place. First of all, it should understand the flow of the English sentence. The flow also should learn. For that, we use a typical language model as just like general language model as LSTM. And another LSTM model, we are going to use it in addition. That is why, okay, if the English sentence is like this, how should I translate this? Okay, I need another LSTM model to decode this. So this is the special case. This is called as encoder decoder architecture. Encoder decoder architecture. So far, the three cases I have discussed, one to many, many to one, and many to many as a standalone language model, you can manage very well with one single LSTM. But your input sequence and output sequence are in a different context. Okay, you cannot manage with one LSTM unit. One LSTM unit is going to act as an encoder, and another LSTM unit is going to act as a decoder. What sort of application comes under that category is one language to another language conversion, chatbot. Because the chatbot, you have a sequence of tokens as a question. What is the corresponding answer for that is? Because your corresponding answer is different from your input question, right? That is why I'm saying not equal. But is the standalone language model is going to understand the sequence of your English test as a time shifted version. A time shifted version. Whatever the sentence is you, right? Your corresponding Y is it's going to be a time shifted version of your same input. But a chatbot kind of an application or a one language to another language application is completely a different logic. So this is a special case like an encoder decoder architecture. Any other application can you think of? Your complete your input sequences and output sequences are different context. Any other application you can think of? Shall I say speech to text, which comes under this category, right? My Tx is not equal to Ty. My Tx is not equal to Ty. Please don't mislead with the represent. I'm not talking about the length of Tx is equal to length of Ty. My representation of input is different from my representation of my output. For these kind of application, your encoder decoder architecture. I will speak a sentence. My model will generate the corresponding text for it, isn't it? Even you can make the reverse of it. I give a feed of sentences. My model will generate a speech for it. A text to speech. Any other application? Text summarization, right? Text summarization comes under this category. What is text summarization? You have a big paragraph of a particular news article, and you are going to summarize this. Because your input, this input sequence is different from this input sequence. You're going to summarize the whole text. Text summarization also comes under many to many, which is a special case encoder decoder architecture. Any other application can you think of? When I present an image, okay, a girl playing in a seashore, I present this image and my model should say, okay, a girl playing in seashore. This is a special type of model. Okay. In a broader sense, I can say one to many. Okay, but here it's a one special case of this, because here I have to use a combination of the CNN and LSTM architecture. We have one case study on this, image captioning. Okay, you have to give a trigger. You have to give a trigger token. Okay, the trigger token is going to come in the form of feature vector. How can I produce the feature vector for this? You know it very well. Any pre-trained model, I can use it. I can take the last layer of my pre-trained model. If I use VGG16, what is the last CNN layer? Just excluding, I just throw the top layer. Top layer is the dense layer I don't want. Access the last layer. The last layer size is 4096 feature vector. apply any input. This feature vector, I'll be presenting this as my one single token, like this, because your one single token can be represented as any size of the feature vector, isn't it? And I can train my model to generate the sentence like this. For this feature vector, you have to generate like the raga example, right? I told you, right? For this raga, the musical note has to be generated. So you're feeding an image, and you're asking the model to generate the sentence. What is the content of the image? That also can be interpreted as one-to-many. I hope you are able to differentiate various applications under the 4 major categories. Okay. And for each application, we are going to see one case study examples. So hereafter, we have enough understanding of the mathematics and the foundation. The remaining sessions are full of implementation one. So we will be having another 3 to, for each cases, we will be having one exercise on it. So language model one-to-many, many-to-one, and this encoder-decoder architecture. Each one we can implement one exercise. But having said that, based on your creativity and all, you can think of multiple projects. Under one category itself, you can think of 10 different applications and all. And there are very limited people have tried. That means if you are going to do one small application based on whatever the ideas I have given, say for example this music generation and all, you can do it as a project, and you can publish that project in an interesting post in a Medium article. You can write it, or you can write it in Analytics India magazine. You write it as a blog post, and that is going to add more credential, like whatever that is going to reflect your learning outcome. So these are all the way you can you have to showcase your whatever the new learnings you have learned. You should take it to your community. You should take this learning to the community. Say, listen here, I have learned this something new idea, and I have implemented for this data set, and these are the results. You can showcase this to the public, particularly in the LinkedIn post and other stuff, article you have written in Medium, and share that article in the LinkedIn post. These are all the way, okay, you can tell to your peer community that you have upgraded your knowledge in these areas. If you come up with any interesting idea which comes under any of these umbrella, tell me in the next session. I will let you know whether this comes under any of these cases out of the 4 major umbrella. You come up and tell me an application. I'll tell you which category this is going to come up. Okay, one is I'm dedicated for encoder decoder. Okay, encoder decoder. It's a special case. This is also a part of many-to-many. Many-to-many. It's a special case where Tx is not equal to Ty. The meaning is the nature of your input sequence is different from the nature of the output sequence. Another branch also many-to-many, where your Tx is equal to Ty. Okay, the nature is same English sentences. You make your language model to understand the actual sequence. Mary had a little lamb, and your output is going to be had a little lamb end of sequence. So that kind of example, simple language model. So let me write this as a simple language model. Another one is one-to-many and many-to-one. Any application by using LSTM or GRU, you tell me, I can put in any one of these 4 subsections. The chatbot, your machine translation, language model, your summarization. So under these umbrella, you can easily come up with your own interesting idea, thought process, and come back and tell me whichever the application what we have not discussed here. Come and tell me, and tell me this application comes under which category. I'll tell you what mode of design you can do. I'll tell you. Any question on this? What kind of application comes in which category? But however, once I superimpose this idea with practical Python notebook, then only you can really appreciate appreciated. Maybe you're now at this point of time, you may try to figure it out theoretically, but once you start doing some exercise, you will have a more concrete understanding of these categories.